Hello, I'm Tianwei Xiong, and I'm glad to introduce our work, GigaTok, scaling visual tokenizers to 3 billion parameters for autoregressive image generation. So in the first place, why do tokenizers need to be scaled up for autoregressive visual generation? The fact is, in current popular autoregressive visual generation projects, their tokenizers are significantly smaller than downstream AR models, and this gap can be as large as 100 times. And with limited parameters, the reconstruction quality can be limited, which in turn restricts the upper bound for downstream generation models. In the bottom right example, the 72 million tokenizer of Llama cannot reconstruct this image well, and even for its T2I version with 50 times data scaling, the reconstruction quality is still limited. The model size of the tokenizer here becomes the bottleneck. So why larger tokenizers were not used in previous work, and how to ensure scaling tokenizers benefit reconstruction and downstream models? This is the problem we want to solve in our work. And we present GigaTok, the first image tokenizer scaled up to 3 billion parameters for better reconstruction and downstream AR generation. In its development, we deal with the biggest challenge for scaling tokenizers, that is the reconstruction versus generation dilemma, where reconstruction can improve with larger tokenizers, but downstream AR models can largely degrade. So what is the biggest problem making tokenizers difficult to scale up? To present the problem, we train 3 tokenizers with 3 different scales and train AR models on them separately. With more parameters, RFID drops, showing the reconstruction is improved, but GFID increases, showing worse downstream generation. And if we look at the cross-entropy validation loss of AR models on the 3 tokenizers, we can find that when tokenizers grow larger, the validation loss increases, which means it is harder to do next token prediction as the latent space grows more complex. So, in one sentence, scaling the tokenizer results in a more complex latent space that is increasingly difficult for the AR generator to learn. Now we know scaling tokenizers can bring better reconstruction but worse downstream generation. And with this in mind, I will present some specific aspects of our designs that lead to the first 3 billion parameter tokenizer. First, design easy to scale architectures. So do we use CNN or transformer or a hybrid architecture? Second, using 1D tokenizers without 2D prior or just the usual 2D token sequences. Third, of course, we want to constrain the latent space complexity. And lastly, how to avoid training collapse when scaling VQ-GAN training to billion parameter scale. So first, for architecture, we use a hybrid one with CNN responsible for spatial downsampling and upsampling, and transformer blocks are responsible for processing the deep features. We only scale up transformer blocks when increasing tokenizer parameters. For 1D tokenizers, we use Q-former as the transformer block, and for 2D tokenizers, we use VIT blocks. We use 1D tokenizer by default, and for our 3 billion tokenizer as it presents better scalability, which we will show later. To regularize the latent space, we align the intermediate 2D features in the transformer decoder to features given by pre-trained dialog V2 using a simple cosine similarity loss, similar to REPA. As it turns out, semantic regularization is the key to restricting the complexity of latent space, and thus enabling the effective scaling of visual tokenizers for better reconstruction and AR generation. There is still one challenge left to train a billion parameter tokenizer, which is the training stability. Here we reveal the importance of entropy loss, which was initially proposed in MACVIT series. To quickly understand what is entropy loss, we can first will the vector quantization approximately as a stochastic step, where the probability of the quantization result z hat being ci given input z is calculated according to the distances of input z to all the codebook vectors. It is an approximate will, as in practice vector quantization is argument and deterministic, not stochastic. With this will, we can calculate entropy loss. Its first term is the expectation of the entropy of z hat given z. This means we want the quantization process has the minimum entropy, so minimum uncertainty and minimum quantization error. Its second term is the entropy of z hat, the quantization result, and this is to make sure the quantization results are evenly distributed across the codebook, increasing codebook usage. And increasing codebook usage is very important for convergence, as we observe that in the early stage of training a 3-bit tokenizer, the divergence of loss happens with low codebook usage, and with entropy loss, the loss can converge with a quickly increasing codebook usage as shown in the figure. With all our designs, we now present the results. First, the semantic regularization is the key to dealing with the reconstruction versus generation dilemma for scaling tokenizers. So from the figures, we can see that with semantic regularization, the blue series have lower RFID and lower GFID, all with an improving trend with larger tokenizers. The validation loss of the AR models also get controlled by semantic regularization. And besides, we show that the linear probing accuracy of the AR models also continuously improve with larger tokenizers if using semantic regularization. So one sentence, scaling tokenizer works with the semantic regularization. One may wonder, why can semantic regularization reduce latent space complexity? We can find some intuition from the visualization of tokenizer features. Here we show the PCA visualization of the tokenizer features of 4 golden retriever images. When no semantic regularization is applied, the features are messy and inconsistent, but when applying semantic regularization, the features show semantic inside a single image and a consistency across the 4 images. These features are less messy and more predictable. Here we continue to show how to better scale up the parameters of tokenizers. We argue that asymmetric 1D tokenizers is more scalable. First, about asymmetric design, we show that prioritizing the scaling of decoders benefits downstream generation more than scaling encoders, and scaling encoders can still bring significant improvements. Then for the choices between 1D and 2D tokenizers, we find that 1D tokenizers show better reconstruction and downstream representation quality when scaling. As for downstream generation, 1D tokenizers present a steeper improving trend than 2D tokenizers, probably because of removing inductive bias in the token sequence structure. So with all these designs, we scale GigaTok to around 3 billion parameters and obtain state-of-the-art reconstruction quality for discrete tokenizers trained and evaluated on ImageNet. Also for downstream models, using a simple AR generator, the 3-bit tokenizer enables comparable GFID to VAR and superior downstream model linear probing accuracy obtained by Lex token prediction training only. To recap, here are important lessons we learned for scaling visual tokenizers. Latent complexity is the key to solving reconstruction versus generation dilemma. Scaling tokenizers works with semantic regularization. 1D tokenizers are more scalable than 2D tokenizers. When scaling tokenizers, expand both encoder and decoder, but decoder needs to be larger. And entropy loss helps stabilize training for billion-scale tokenizers. That's the reference, and this is the introduction, and thank you for listening.